Hello, everyone, and a very good morning to all of you. Distinguished delegates, speakers, and participants from SAARC member states. Ladies and gentlemen, I am very thankful to all of you for joining us in this online training. My name is S.N. Javed, and I am working as a research fellow renewable energy at SAARC Energy Center, Islamabad. I shall be moderating this training, which will be broadcasted daily starting from today till Friday, 3rd December, from 10 o'clock to 12 o'clock every day. I am grateful to our elite panel of experts such as Dr. Peter Lilienthal and Silva Navarro for their willingness to participate in this training. With this, now I may like to request Dr. Nawaz Ahmed, who is the director of SAARC Energy Center, to give his opening remarks.
Thank you very much, Asan, for your introduction and holding this training session. Dear participants and presenters of the training, good morning, everyone. I, Dr. Nawaz Ahmed, as Director SAARC Energy Center, welcome you all to this training session on HOMER software. Ladies and gentlemen, SAARC region represents nearly 25% of the world population, and energy security is an important agenda for prosperity of the SAARC Asian region. The SAARC region has significant renewable energy resources. If properly developed, these could greatly reduce dependence on imported fuel, diversify energy supplies, improve energy security, and help lower the high electricity costs. Recognizing the growing importance and role of renewables in the overall energy mix and enhancing needed essential skills in planning and management of renewables, SAARC Energy Center has organized this online training program on HOMER software. HOMER software navigates the complexities of building cost-effective and reliable hybrid, microgrid, and grid-connected systems that combine traditionally generated and renewables. With over 250,000 users, HOMER is an established global leader for design optimization and feasibility. Dear participants, the SAARC Center has organized this training for capacity building of professionals in the SAARC region. For the purpose, we have engaged Dr. Peter Lilienthal, who is currently Global Microgrid Lead for UL LLC. Previously, he was the CEO of HOMER Energy. The other trainer with us is Engineer Silva Navarro, who is a renewable energy consultant and is a trainer of HOMER software. In this 5 days training program, HOMER software will be introduced. Its key parameters and tools will be presented by the experts to the participants. After attending this training, it is hoped that the participants shall be able to design renewable energy systems independently using the HOMER software. In the end, I thank you all for joining this training session. I expect this event to be an interactive session, so please feel free to raise questions and join the discussion. With these words, I declare the session open and wish you all a very comfortable learning and knowledge sharing experience. Now I request Mr. Asim Javed, a research fellow at SAARC Energy Center, to take us through the agenda. Over to Mr. Asim Javed, and thank you all again.
Thank you very much, Dr. for your kind words. So now we will move on towards the agenda. The first, this session would be, the presentation will be given by Dr. Peter Lilienthal. He will be speaking on the foundations of HOMER Pro 1 software. The contents of his presentation would be on the introduction to HOMER Pro, demonstration of simulation and optimization, modeling small community systems, simulating a diesel system, building hybrid microgrid with solar PV, sensitivity analysis, payback, and internal rate of return. I will briefly introduce Dr. Peter Lilienthal. He is the global microgrid lead for UL LLC. Previously, he was the CEO of HOMER Energy since 1992. He has been the developer of National Renewable Energy Laboratories HOMER Hybrid Power Optimization Software, which has been used by over 250,000 energy practitioners in 193 countries. NREL licensed Homer Energy to be the sole worldwide commercialization licensee to distribute and enhance the Homer model. Dr. Lilienthal was the senior economist with international programs at NREL from 1990 to 2007. He was one of the creators of NREL's Village Power program. He has a PhD in management science and engineering from Stanford University. He has been active in the field of renewable energy and energy efficiency since 1978. This has included designing and teaching courses at the university level, project development of independent power projects, and consulting to industry and regulators. His expertise is in the economic and financial analysis of renewable and microgrid projects. I would now request Dr. Peter to start his presentation. Over to you, sir.
Well, thank you very much, and thank you all for all you attendees who are here. And give me 1 second here while I share my screen. Hold on a second. People can see your screen. Which screen?
We can see your screen, sir.
Well, I have more than one screen, so I have to make sure you're seeing the right one. Sorry about that. So which screen do you see? Is it just says Foundations of Homer Pro and nothing else, or does it have other stuff on it as well?
Just the Foundations of Homer Pro.
Okay, good. Well, thank you. Okay, so now I move on to the next slide, and I just want to help everybody out here before we begin, so that they can see how to handle, in case they have never used GoToWebinar before. Here are the controls. The most important one is the ability to raise your hand in the chat window. If you want to send us a question during the training, we will collect them, and if they're a clarification of something we're talking about right at the moment, we'll try to deal with it in real time. Otherwise, we'll keep what we call a parking lot of questions to address at the end. So you can see here some advice on how to handle the GoToWebinar. Also, we've arranged for everyone to have a license to Homer for the next 7 days. So hopefully you've gone to homerenergy.com and downloaded at least the trial version. And you can activate it by going to Help License, and then clicking on this little button here that says Concurrent, and typing in, typing in this number here, which I will put in the chat. Actually, that would be useful for me to do that. So I am going to leave, let me cut and paste this into the chat window. Send to, oh, huh. Well, here, I'm going to send it to the organizers, and I'm going to ask them to, evidently, I can't send a chat to everybody, but they can. So hopefully they'll forward that to you. Sorry about that. Let me go back to the presentation. So we've arranged for everybody to have a license to it. And if you have any trouble with this, I've got a couple of my colleagues online here who will help. So the objectives of the next 5 days is to describe for you Homer Pro's, what we call a simulation, optimization, and sensitivity paradigm. These are 3 different functions, and they're nested within each other, and it's kind of a unique paradigm that Homer has. And so we want to make sure you understand that. And familiarize you with the user interface, show you the steps to run a complete initial analysis with HOMER Pro for several different kinds of projects. And then how to develop a model, a more detailed model, both a conceptual model and then a more detailed model based on real sizing and capacities of equipment, and the whole design process, which is very iterative. So you build a model, you look at the results, you modify the model, you iterate like that until you've refined your design. And we encourage you all to ask questions as we go along. I'm going to describe the first three sessions, today, Tuesday and Wednesday. And today we're going to focus on just a quick design for a basic model. We're going to start with just a really simple diesel-only system, not because we recommend that, just because we're going to build up the system starting with the simplest one. Then we're going to add batteries and optimize the number of batteries. Then we're going to add PV and optimize that. And then we're going to perform some sensitivity analysis to see how changes in the fuel price or the desired reliability can affect the results. So that's today's agenda. Tomorrow, we're going to do more by looking at how you can modify the loads, either creating a synthetic load or importing load data. We show how to size a generator. We have several different ways of modeling and sizing backup generators. And we're going to refine that design that we created today. We're going to refine that tomorrow, including sizing the converter and additional sensitivity analysis. On the third day, we'll get into grid-connected systems, looking at net metering, feed-in tariffs, and build a whole solar plus storage grid-connected system. So that's the agenda for the next 3 days. On the fourth day, we're going to do more detailed wind and solar modeling. And on the fifth day, we're going to look at larger systems that might have multiple generators. So this would be appropriate for some of the island systems where you've got a real utility with multiple generators, or any isolated town that has a utility plant already, in which case it would usually have multiple generators. So before we start, I just want to give a little background on who we are. We're part of UL Renewables. So UL is a company based in the US. It was founded in 1894 to certify the safety of electrical equipment back when electricity was new. And so in the US, every single electrical appliance is certified by UL, has a little UL sticker on it. And they've expanded over the years to do safety testing, inspection, and certification of a huge range of products. Over 2 billion products are certified by UL. And we've grown to 14,000 people, and we've expanded internationally with offices in over 100 countries. The dots on this map are just some of our bigger offices in Dubai. We have a couple in India, Singapore. And then starting about 12 years ago, UL expanded its concept of safety to include sustainability. And so they've acquired several renewable energy companies, AWS True Power, which is a leader in resource assessment, the Deutsche Energy Wind Institute, which is a wind certification. And then in 2019, they acquired us. The renewables section has over 600 people. UL as a whole is 14,000 people. We work on 70% of the wind projects in the US, and as you can see, projects all over the world. We're actually part of what's they call the advisory services, which has a full range of services to help with developing renewable projects, from feasibility, early stage conceptual designs, the actual development process. We do a lot of work with banks on due diligence and independent engineering, construction monitoring, and then asset management operations. Repowering is a big aspect of their work. So I just wanted to give you an overview of UL. HOMER Energy by UL. HOMER stands for Hybrid Optimization of Multiple Energy Resources. So we're technology agnostic. We're the exclusive developer and distributor of the NREL, with the NREL license from NREL, for the HOMER software suite. And as the Hassan was saying, we are trusted de facto global standard for hybrid systems and mini grids and microgrid designs. I originally created the HOMER software back at the National Renewable Energy Lab, starting in 1992 as a result of the Earth Summit in Rio that year. Oops, I didn't mean to do that. And it was basically a research project in the early 90s, but by the late 90s, we converted it from using specialized optimization software running on a Unix workstation that only I and maybe one other person could use. We converted it to a Windows app with C++. We were able to put it on the web so people could download it, and it kind of started snowballing, the gaining momentum, etc. And we've been enhancing it ever since. But in 2009, I saw the commercial potential for it. It wasn't really a research project anymore. And NREL is really ideal for doing research, not for doing commercial activities. So we privatized it in 2009. I created HOMER Energy with the exclusive license. And for 10 years, we grew that. But in 2019, we were acquired by Underwriters Laboratory, which has given us a lot more resources, a lot more. Well, the global offices is a huge help. So just a little snippet of, on the left there are just some sample of our users, but on the right is a map that shows, at this point, it's over 100,000 independent analyses that have been done on microgrids around the world. And you can see, of course, India is a hotspot, and you can see where other hotspots are, where a lot of activity happens, India and Bangladesh, and the Maldives, but it's hard to see that on the map, and the Philippines and Indonesia and Australia and East Africa and West Africa. Anyway, so we're used all over the world. So let me explain a little bit before we get into the software itself, just to give you a sense of some sort of background and overview of it. We have three pieces of software at this point. HOMER Pro is sort of the one that's been around the longest. It's kind of the flagship. It's the most flexible, but it is ideal for standalone microgrids to determine the least cost way to provide to serve a load in remote areas, energy access challenges, islands, and things like mines and et cetera, campuses. It does have some capability to do grid connected projects, which we will be showing on Wednesday. But we developed another product, HOMER Grid, explicitly for behind the meter grid connected projects that includes things like demand charge reduction. Where I added a line here, which oh, there it is. Huh. But it got animated. Electric vehicle charging stations. I didn't realize I had animated that. Tariff modeling, value stacking. This is really for focused explicitly on behind the meter distributed generation projects. And now, as we're part of UL, they've got a lot of experience with large utility scale projects that are front of the meter. So we've created a new piece of software called HOMER Front. It's currently in beta testing. It'll probably be January before it's broadly available. We've got a limited number of users, giving it a workout before we make it fully public for large utility scale hybrid projects, because storage has gotten so inexpensive and the penetration of wind and solar has gotten so high that storage has now become an important large resource for large grids. But that's not what we're going to focus on today. I just wanted to give you sort of an overview. The fundamental goal of HOMER is to answer this question of what's best. what should we do here? What's the best thing that we can do here? And it'd be great if there was a one-size-fits-all solution. It's kind of like the Ford Model T that got the auto industry going. If you could, there was like what we call cookie cutter solutions. You could just do the same thing over and over again. But that's not really true, because it's very, very site specific. The answer, unfortunately, is that it depends. It depends on what are the resources in the local area. It depends on your load shapes, not just how big the load is, but the shape of the load, its seasonality, its daily profile, etc. It makes a big difference to the design of a standalone power system. And of course, equipment prices and performance, they're improving at a rapid rate, which is great, but it actually adds a little bit of confusion because things are changing. Something I learned a long time ago, it's become sort of a mantra, that's a confused mind says no. So we are really going to try not to confuse you all here. And we hope the goal of HOMER is to help people understand what are these hybrid systems, what do they look like, so they're not confused, so that you can move forward. So I like the little puzzle picture here where HOMER fits the pieces together. Well, so I think it's really important to understand the design process, which we think is very, very iterative. So we've got a little circle there. You collect data, you analyze it, you evaluate it, you improve your model. You start with really some starting idea. I want to do renewable. I think renewable energy would be a great way to a great project to have for this community. But that's just an idea. And eventually you want to have a design that you can build. But in between, there's all these steps. So you have an initial concept, you refine it, you get down to design, and then eventually you get to a detailed design. And so in each one of those steps, you're doing iteration after iteration. So in the early stage, you have a lot of options, and you want something that's quick and easy and doesn't cost much, because maybe it's not a good project at all, and you don't want to spend a lot of time on it, or it's going to cost you a lot of resources, a lot of time and money to get better data, but you want to get some idea. So that's at the early stage. It's really important to be able to move along quickly, and we hope that's what we've accomplished with HOMER. But we've made it so it can accept data and multiple levels of detail. Later, you're going to want to be able to talk to potential vendors intelligently. They don't want to talk to you unless you've got a fairly concrete idea of what you want. So you want more detailed designs. You want to be able to put in specific equipment choices, specific sizing, and it's just a much more detailed analysis. So at that stage, HOMER will take more detailed data. Now, in the final stages, there's things like, what size wire do you need, or then there's for larger systems, there's issues about things like transient stability, power flow, etc., that are more about distribution planning and the actual construction process as well, lightning protection, that sort of thing. So HOMER Pro doesn't do any of those things. So it's not like HOMER Pro does everything, but it really nails the initial design and some refinements of those initial designs right up to the point where you're talking to an EPC about actually building it. So this paradigm I mentioned before about simulation, optimization, and sensitivity analysis I think is really important to understand what's going on inside HOMER. So at its core level, it's meeting the load chronologically. And so, typically we do 1 hour time steps for a year. We can do any size time step down to 1 minute, and we can go out to 30 years. But regardless of that, it's stepping through chronologically and simulating how a power system would operate. when you charge the batteries, when you discharge the batteries, obviously it's getting this resource data from the solar or wind or whatever. And if you need backup generation, when and how much fuel is that going to use? Does that, excuse me, steps through an entire year, at least 1 year, how the system would actually operate. So that tells you how much fuel it's going to use, how much wear is on the battery, et cetera, for a particular design. So that's one design. So the optimization loop around that does that for hundreds or maybe thousands of different system designs, and then ranks them by total cost of ownership. We call it net present cost. Some people call it life cycle cost. Some people call it total cost of ownership. We call it net present cost, all the same concept. So that's the sort of default ranking. The least cost system sort of is at the top of the list. You can reorder that list and rank it in other ways as well, but that's the default, and we think for a very good reason. So that tells you what's best for a particular scenario. But what if fuel prices change? Or what if you really weren't sure, like in the beginning of analysis, what different things cost, but you want to get some results, and you want to see, like, maybe there's a price for the batteries above which it just doesn't make sense to have batteries at all. That's important to know. So sensitivity analysis can be used for a lot of things. We've built it in so you can do it automatically. And we think it's really important, especially when there's a lot of uncertainty. And when you're developing small projects, especially in rural or remote areas, there's always going to be a lot of uncertainty about a lot of things. But you don't want that to, stop you in your tracks. You want to still be able to move forward. So that's the simulation, optimization, sensitivity analysis. So you'll see a lot more of this over the course of the next 5 days. You've got input data, you get results, and the results. Actually, I have a better slide for this. So let me right here. So the inputs are things like the economics, interest rates, etc. The load profile is crucially important. We make it pretty easy to get renewable resource data like the solar data. And then what components, are you going to consider wind, for example, or not? Are you, so you have to tell HOMER what components to consider. Then it does this analysis I was talking about, simulates one system, does that for many, many systems, ranks them. And then if you've done a sensitivity analysis, it'll do that all over again, changing whatever, fuel price or whatever you want to do a sensitivity analysis on. And you get results, you get financial results like the internal rate of return or the payback period. You get system sizing, what's the least cost size of your PV array, your battery bank, et cetera. And you can drill down and look hour by hour or minute by minute if you had that kind of data, input data. How did the system actually perform? So you'll see all that in a minute. So we'll get started really soon here. I do want to, and we'll mention this again, but I do want to point out we have quite a bit of support material, and you can go on our website here, homerenergy.com/support, and it's also built into the software. There's a user manual, there's knowledge base, there's we have a library of videos. We can actually help you if you hire us to work with you on an advisory basis. And we have several people in the region. Needy is here, she's in India. I believe Zaid is here, he's in South Africa. Silver is in the Philippines. Actually, we have a fairly substantial Indian office in India. And we do training like this here. We also have a getting started guide built into the software, sample files, and a tutorial all built in. And you can always email us at support@homerenergy.com. So we should jump into this software training here. And I'm going to turn it over to Silver Navarro. He's been using HOMER now for, I don't know, 25 years, maybe more. I've worked with him right from the beginning back in the 90s at NREL. And I don't actually have his bio in front of me, but he's certainly very experienced and has done a lot of Homer training. And I'm going to turn it over to you, Silver.
Thank you, Peter. Can you hear me?
Yes.
Yes. So I'll just share my screen. Okay, can you see my screen now?
Yes.
Okay. So just
And you might want to first go to help and show the what I was just talking about under help before you get started.
all right. So this one.
Well, all 5 of those are useful, I think.
Okay. Yeah. So first we look into this help file. So it provides information about Homer, and you can browse through this help file. You can also type in the specific topic you want to review, and then we can look into take your tour. So if you want to go through the software, it will help you go through this process. And you also have the setup assistance. Okay. And information about Homer. So it provides you what modules are included in your copy, and about the uh, product license. It also provides you when will be the expiration date of your modules.
And you might point
Yes,
out
Peter?
the concurrent button at the bottom. That was where
Okay.
you type in that number.
Yeah. So for a purpose, there's a concurrent button at the top, at the lower part of the manage license screen. So Peter had already posted the number. So because we will be using the Homer software throughout the week, so we hope everyone will have an actual use of the software. It's a way of the best way of learning the software really is to practice this. So there's a concurrent key that you can type in the number so that you'll have a licensed Homer software for the course. Okay.
Yeah, and that setup assistant is like it's like a wizard. It walks you through a process, very simple process.
Okay. Yes. So sorry for that. Okay. So we have. Shall I start?
Yeah.
With okay. So this training course, I would first explain is a way of learning the Homer Pro software by actually using it. And as Peter mentioned, it's a step-by-step learning, so everyone will be on the same page. I believe some of the participants already used Homer, but we wanted to have everyone to have an equal footing and experience and user capability regarding the Homer software. So we have prepared a simple manual for this particular course. So this specific manual is designed for the version 3.14.4 of Homer. Because some other guides may be using the older software. So for the basic uh, training, we'll start with a blank Homer file. Then we start by typing the location of a project. In this case, we're using Nairobi, Kenya. So I'll go to my HOMER software and type in that specific site. So just an example. And then we can click on location search. And it goes to that specific site on the map on your right. So you can click on the aerial view of that site, or you can zoom into the specific neighborhood of that that site. Okay, so that's let's say that's where we wanted to have our system. Now we can name our project sample project. So if we look into the load, as Peter mentioned, we can
Silver, you want to
yes.
grab the resources?
Okay. Yeah, I'll do that in a while. So first we have this site, and I will start with the load because that's anyway what we are supposed to provide power with. So we can look into a community load. There are a library of loads you can select, and then starting from a residential load like a small house, a commercial load for a commercial building, industrial, and community. For this case, we can use the community and click OK. Right, so when we click OK, just to explain on the load profile, so on this screen you can see the hourly kilowatt data or the demand of that community or that village. So early in the morning, there's small load, and then it picks up during the early on the morning, the daytime, and then at night you have more loads because of lighting loads, and people go home and increase their demand, and goes down at the end of the day. So you also have the D map just to show you the intensity of the energy demand. So the bottom part is the early morning, the middle part is the noontime, and evening on the upper part. So there's a high demand during the evening time. In a typical village, you have this type of load. So basically, for remote installation, you just install a diesel genset. So to do that, you can click on the components and add a generator. Now, HOMER can provide you an auto-size genset. That means if you don't have any idea how big is the genset, HOMER can guide you by using an auto-size genset, and HOMER will look into the best size that you can use for that particular load, the village load. So you can add this generator. So this diesel genset has a default parameters already. So it has an initial capital of $500 per kilowatt. That's a rate per capacity. And the replacement cost is also 500. And for operation and maintenance, it has a default value of $0.03 per hour. And in this default case, the typical fuel price is $1 per liter. You can actually change this parameter, but for this case, we'll use the default system. So if we click on the calculate, because we have a complete system already, we have a load and we have a genset, HOMER will go through the iterations, calculation, and then it will display you the summary of the simulation results. So in this screen, you can see the architecture of the system that will run the load that we selected. In this particular case, you have a 23 kilowatt genset. And the first screen you will see is the cost. So you can see the cost components. So you have the initial capital of buying the genset. Then on the operation, you have the fuel cost and also the replacement cost of the genset. And this particular project has a time frame of 25 years. So during the replacement process, you may have a salvage value of your equipment after the 5th year. So at the end of the 25-year project time frame, you have a positive salvage value. So that's on the economic side. The second tab is on the table. So HOMER displays this particular architecture of the system that we have modeled. So under the auto size genset, HOMER selected 23 kilowatt genset and calculating all the economics, including the capital cost and the O&M and the fuel price. The result is a net present cost of 529,432 US dollars. In terms of cost of energy, the cost is 0.678 US dollars per kilowatt hour. And you can have an annualized operating cost of 40,664. So it will also show you how much fuel was used for this particular configuration by the genset. In this case, it's using 27,652 liters of fuel. Since it's a single source power system, or that means it's only getting energy from the genset, your genset will be running for the whole year, or 8,760 hours a year. Of course, this in actual practice there will be maintenance a downtime, but in this case it's a simulation that we can run in ideal condition. So we can double click on this result, and HOMER will display more detailed result of the system simulated. You have a cost summary, so you have the auto genset replacement cost and O&M cost, and also the cost for the fuel and the salvage value. That's on the first tab. We'll have more cost details as presented earlier on the cash flow. For compare economics, this is the base case we're establishing, so there's no other systems we are comparing with, so it's not applicable at this point. And on the electrical side, HOMER displays a monthly performance of your system. So in this case, we have a genset running throughout the year, and it follows whatever load is needed here. So it's only 100% of the energy was supplied by the genset. And you can see also that there's an excess electricity on the upper right part of the screen, because this is because of the energy conversion efficiency of the genset, as it's more efficient during when it's loaded higher, and it has a minimum required load. So if the load is smaller, the conversion efficiency of fuel to electricity is lower, so you will have some excess electricity as high as 13% in this case. So that's the basic electrical output. Fuel summary is also used, so you can see how much fuel is being used throughout the year, and also throughout every month. And the auto size genset performance is also shown here. So how many hours it's been running and how much fuel had been consumed. So regarding emissions, based on the contents of the fuel, it can also show you how much CO2 had been emitted, carbon monoxide, also unburned hydrocarbons. particulate matters, sulfur dioxide and nitrogen oxide. So for environmental studies, HOMER will be also useful in establishing a baseline for diesel-only system. Okay, so in this case, we have a basic system already. So just to have a feel on the environment of the HOMER Pro, we can click always on the home screen to show our configuration of the system. So we have the load, the genset, and also the map. Okay, so as I mentioned earlier, it may be uh, possible to include a battery in this system just to uh, address the efficiency of the genset. So we can add a storage battery, and we can, let's say, use a lead acid battery to charge the battery when the load is low and use that energy when uh, uh, the battery is full and there's added capacity to be used in the system. So we can add a storage battery. Again, there are default battery types that HOMER can provide in its library, but in this case, we'll just use a lead acid battery. So like the genset, we don't know maybe how much battery we need, so we can use the HOMER optimizer for the sizing of the system. And on the left side, you can see that there are warning signs. So the green one, it's a recommendation. So that's like HOMER is recommending to add renewable energy system. We'll do that later. And you can see the orange warning as input does not match the current results. That means there had been modification on the inputs that we did. And on the red alarm, alarm button, it's showing to add a converter. So it will not proceed unless you address this warning. So as we know, batteries produce direct current electricity, so you cannot directly couple the battery to our system. So we need to add a converter. So we can click on that warning sign, and HOMER will lead you to how would you address that specific issue. In this case, we need to add uh, a converter. So by clicking on that button, HOMER easily provided a solution. So we have a converter in between the battery and the AC bus. So converter in this case both acts as a charger or a rectifier that will convert excess energy from your AC system and convert it to DC to charge your battery. And on the other end, you can also convert or invert DC voltage from your battery to the AC bus. So it's a bidirectional inverter or converter to couple the AC bus and the DC bus. And we can also use a HOMER optimizer for the sizing of the system. Okay, so if we click calculate, because we don't have any red warnings anymore, HOMER will try to simulate what if we add the battery to our diesel-only system. And then it gives you a table of the results of the architecture, and it is ranked according to the lowest cost of energy or the lowest net present cost. So if we look into the previous system that we modeled using a 23 kilowatt genset, our net present cost is 529,442. But adding a battery that HOMER modeled, and it's recommending to use 37 pieces of 1 kilowatt hour lead acid battery and use a 5.17 kilowatt converter, our net present cost went down to 465,621, and our cost of energy also dropped. So what happened when we added the battery? It actually reduced the fuel cost. So if you look into the fuel, without the battery, the system consumes around 27,652. But with the battery, it efficiently utilizes the genset to fully load it and release that energy whenever needed. So there's a reduction of fuel cost. So this basic exercise shows us that adding a battery and inverter charger to our existing diesel system would actually reduce our cost of energy. But with that added component, our initial capital, instead of having just a genset of costing us 11,500, we added batteries and inverter to the system. So our capital cost now went up to 24,000 US dollars, 24,150. If we look into the economics of the system, we can double click on that solution that we looked at, and then we can look into compare economics. So HOMER uses our previous genset only component configuration or architecture as the baseline. So with that baseline and with the additional capital cost that we will spend for the battery and the inverter, Homer calculates the economics and look into um, the present worth, annual worth, and especially the return on investment of that additional cost of the battery and inverter. So in this case, the ROI is 42.4. The internal rate of return is 58.9, and the simple payback is 1.36. So with a discounted payback of 1.4 for 2 years. So that means even if we add a battery and inverter with additional cost to the system, Homer simulates that we can recover that cost within 1 year, 1.36 years or less than 2 years. So it's a good investment if we consider adding battery and inverter to the system. Okay. Okay. So that's one way Homer can help you decide if it makes sense to add battery and inverter to the system. Okay. Any additional inputs, Peter, if you want to contribute?
Well, I just want to point out that this is the optimization table. You might click on the overall button in the upper right just to show that it looked at many different battery sizes.
Okay.
But it's just showing you the best one. So,
Okay,
so
thank
you
you,
can
Peter.
see it tried in all different battery sizes and converter sizes to find the least cost system which is at the top of the list. But this list is unwieldy. It's so long, so big that we have the categorized option to so you can easily see. It sorts things for you, very helpful.
Yeah. So
Other than
thank you,
that,
Peter. Yeah.
that's good.
Okay. So as Peter mentioned, Homer provides a lot of simulations of different sizes of gensets, the battery, and the converter, and ranks them according to the lowest net present cost. So since this is a very long list, we can click on the categorized button here just to categorize the architecture of having a diesel-only system and having a diesel with battery and converter system that with the lowest net present cost among the list of tried systems or configurations. Okay, so if we go back to the home page, then this is our architecture now. Uh, the next thing would be, what if we add solar to our installation? Because solar is a very popular technology now. It's the cost has dropped. So under components, we can click add solar. So we have a generic flat plate solar, and we can click add PV to add PV to our system. So as you can see, there's a red warning sign. So it's telling us add a solar GHI resource, because for HOMER to model how much energy will a solar generate, it needs to have that solar resource data, or the global horizontal radiation data resource. So we click on that warning sign, and it brings us to that resource GSI resource table input. So we can click on download from internet, and it will give us a choice of having solar from NASA or from NREL. So in this case, we'll just use NREL. It's using actually the location that we used earlier in Nairobi, and the software looks into the specific solar irradiation data of that site. So then we can download the data for our site. Okay, so if you're connected to the internet, you can easily download that. And shown in the screen is the solar resource data on a monthly basis. So there are months with low solar irradiation, and you have a middle line there showing the clearness index. So this is very important if you're using concentrated PV. Now we have a solar resource that we can use, and we can check on our PV system. So again, we can use HOMER to select the size for us. So if we click on calculate, because there's no red warnings anymore, HOMER does iterations of different configurations, and this is why it will take a few seconds to look for the best configuration of utilizing all these technologies that we provided HOMER to use. So it ranks the different configuration according to the lowest net present cost. So we have the categorized list, and the lowest in the list is the lowest NPC on the list is a system architecture with 28.8 kilowatts of PV, and then still using the 23 kilowatt genset that we previously modeled. But in this case, it's using more batteries, 96 pieces of 1 kilowatt hour lead acid, and a larger converter of 15.3 kilowatts. And now the cost of energy had been reduced. But of course, with more additional component, our initial capital had also increased from the previous 11,000. Now it's 117,000 to 427. But on the long run, throughout the project time frame that we established for 25 years, the system has the best or the lowest cost of energy based on the lowest net present cost. So if we look again into the economics of this system, we can double click on that particular architecture, and we can click on the compare economics. So looking into the system using the diesel only system as a base case, our investment has a payback of 5.31 years. It's a longer recovery period, but the cost of energy is much lower than the basic system that we showed earlier. So HOMER also provides different configuration. So if you remember our previous configuration of just adding a battery and inverter to the system, it ranks second among the architecture. And having a system with diesel converter without batteries provides you a higher cost because of uh, the lack of storage. And if you want to have a system that runs totally on renewables without the diesel, you can see that architecture at the bottom of the list. It's on the bottom of the list because it has the highest net present cost or the highest cost of energy. Of course, can consider this as the cleanest among the options, but with the highest cost of energy. So without, let's say, considering the economics and only looking into the environmental side, we may use this last option. But we have the highest cost of energy. And the quickest configuration we can use is just having the diesel. So HOMER provides you an idea of what different configurations can be done. These are configurations that will meet our requirement. At the same time, show us the economics of running those systems. We have conveniently used the feature of HOMER regarding auto sizing, because then HOMER can guide us what size to use. So any inputs from you, Peter, at this point?
No, this is good, and it's a good segue to the sensitivity studies, sensitivity analysis we're going to do soon to show how those results change with either fuel sources or a lot of people are interested in that 100% renewable solution, which this analysis shows isn't very attractive because it's twice the price, the total cost. But we can show how we can lower that cost using the sensitivity analysis on the reliability. So I think, well, that may not be the very next lesson. It's coming right up, though.
Yeah, okay. Talking about sensitivity, that's a good segue towards that towards reliability also. There's always a question: what if any of these parameters change? What we can play on the fuel cost. How would the configuration of our system change if the fuel cost is higher? So, as mentioned earlier by Peter, HOMER does not only simulate the system, but it can also do sensitivities. That means if one parameter changes, how would the optimized system would look like? So to look into sensitivities on the fuel cost, we can go back to our genset, and for the fuel price, we can go to the advanced setting, and we have here a diesel fuel price with a default of $1 per liter. So sensitivity can provide you different values for that. So what if fuel price goes down, say $0.8 per liter? Or what if it goes up to let's say $1.5? In some cases, fuel is quite expensive, not only in the cost of fuel, but the cost of transport, the cost of losses of or spillage along the way. So it can increase. So we can put these sensitivities as an option to see what if fuel price would change. How will the configuration also change? Okay, so we can click on the calculate button, and HOMER will simulate the different configuration using the different sensitivity values that we provided. In this case, we provided three fuel costs. So the cheaper one, what if the fuel becomes cheaper, then the baseline of $1 and the higher fuel price. So the baseline that we established is in the middle part. So the screen now shows you different sensitivity configuration. So based on our fuel price, on the top row, we can see that the fuel price is 0.8, and the best configuration if the fuel price is cheap is a 27.4 kilowatt PV, and using the same 23 kilowatt genset. But if the fuel price goes higher to 1.5 US dollars per liter, so instead of having just a 28.8 kilowatt peak of solar for a $1 per liter fuel, it tries to use more solar modules because of the higher fuel price. So you can see that if one parameter changes, the configuration also changes. So if we look into higher fuel price, the configuration of different architectures also changes. So just to have an overview of what configuration would, how the configuration would change with different sensitivities, we can look into the graph. And let's say it's not that.
You can do a line graph. Go to the upper right and do a line plot.
Okay, yeah. Line plot. Okay, so we can see here 3 points for our fuel. So the middle part is the default $1, and the right part is 150, and the cheaper fuel is on the left. And on the left column, you can see the net present cost of the system. So obviously, with the increasing cost of fuel, our net present cost also increases.
But you know, for the secondary variable, put something like fuel consumption or fuel cost on there. Fuel cost right there, yeah. Well, or fuel consumption might be better actually. Fuel, total fuel there, down for fuel, total fuel.
Okay. Yes. So thank you, Peter. So as the fuel cost increases, HOMER tries to reduce the use of the genset and thus reducing the fuel consumption. So, but if fuel is cheap, it makes sense to use that fuel more.
Yeah, and Silver, you know, another one you could put on there is operating hours or run hours of the generator, and also, yeah, just I think that instead of total net present cost, put, you know, I have to scroll down a little bit. Where is it? There it is, gen hours. up a few gen hours.
Okay.
Yeah, there. So the generator is running less. And another graph I think that's really useful is if for primary and secondary, you put in the PV capacity and the battery capacity. Yeah, no, for the variables to plot. Yeah. So,
Okay, so we look into the PV capacity.
And on secondary, put the battery capacity.
Okay.
Yeah, there's in there somewhere. LA quantity. Yeah, there it is. The first one. Up.
Okay, thank you. Yeah.
And they're parallel.
So,
Well, not always parallel, but yeah.
yeah. So as I mentioned earlier, when the fuel cost is higher, Homer is recommending more on the use of the PV. And with the increasing capacity of PV used, the number of battery also follows. As mentioned by Peter, it's a parallel line. So this is the trends that you can see with the sensitivities as the fuel cost increases. Homer is recommending to use less of the genset because of the fuel cost and replace that with more PV on the system. Okay, so in our configuration, we still have the same configuration. So we can look into the system reliability because as I've shown earlier, the genset only system was running at 8,760 hours. Well, that's quite unrealistic in the real world. So what if we allow a downtime? That means part of the load will not be met. So that happens even the grid code allows that. So we can look into the project and we can click on the constraints. So on the top, you can see maximum annual capacity shortage. For initial run, we're using 0. That means there's no outages and all the loads are met. What if we introduce some outages or allow outages? So we can click again on the sensitivity and we can add, let's say, 3% or and also 5% acceptable outages. So if we run, Homer will have sensitivity on the fuel and also sensitivity on the um, annual capacity shortage. So just to have a look into what will be the effect of the maximum annual capacity shortage on our system, we can remove first the sensitivity on the fuel, and we just use the $1 per per dollar per liter fuel cost, just to isolate the sensitivity on the fuel against the sensitivity on the reliability. So one way of also looking at this is to click on the sensitivity icon here. And as you can see, it shows us the sensitivity only on the capacity shortage. If we have not removed the sensitivity on the fuel cost, it would be another column on this screen. So if we run into the calculation, just to have a feel of how will the configuration change if we allow capacity shortage. So this is also an economic issue because 100% system would be very expensive as we can validate. So if we go back to the tables screen, we have different sensitivity uh, or sensitivity for the capacity shortage. So with a uh, a total system with no shortage, the capacity of PV stays the same.
So Silver, do a joint sensitivity and put the fuel back in.
Okay.
Because the combination of expensive fuel and allowing a little bit of capacity shortage is when things really change.
All right. So we will add, yeah, thank you, Peter. So you can see the sensitivity is not really affected by just the capacity shortage alone. But if we look into the fuel cost sensitivity in combination with uh, the capacity shortage, so we could add again and 1.5. So click on the sensitivity. So we have two columns now on the fuel price and on the capacity shortage. Click calculate. Then HOMER looks into the whole combination of those two sets of sensitivities. So it will take some time for HOMER to simulate those two sets of sensitivity. It depends on how fast your computers will be, but in this case, we're running it real time and will be done in a few seconds. Okay, so now we're done. Now we have the numbers here, and this can easily be, uh, say, interpreted if we look into the sensitivity. Uh,
You might try a broader sensitivity.
with what value, Peter?
Well, I'm looking it up here. Because we have
The capacity shortage
yeah
is maybe 10.
yeah go to a higher fuel price and a higher and a higher capacity shortage.
Okay. Right. So if the difference is not that big, configuration does not really change. So we can look into uh, search space. Go back to the, okay.
Yeah,
Yes.
and put in
And
250 of fuel for fuel price, which I know is really high, but and 10, just add that to, 10, put 10% there and 2.5 there. I know that's really high, but just to demonstrate the impact is worthwhile.
okay. All right. So
And then recalculate, which will take a minute. Is true.
yeah. Yeah.
It's searching for the lowest cost system, and it's trying. So you've got all these different sensitivity cases. It's got a couple of different dispatch strategies that it's looking at, and so you can see each one of those little boxes is a separate optimization, and the numbers there show there, several hundred simulations in each of the optimization.
Excuse me, just for the information of all the participants, we are receiving your questions and we will address those questions at the end of the presentation at 11:50.
Yes, so we could spend time for questions. I
Okay.
think at the end of the session, we'll just complete this simulation because we have shown the basic setup of load and genset. We have added batteries, we have added solar, we changed the fuel cost, changed the sensitivity on the liability. So we'll give time for the audience to raise their questions so we can respond to them.
Yeah, but Hassan, we can't see the questions. So I don't know if you can cut and paste them into the chat or something.
Okay, what I can do is I'll just copy paste those questions to you on the chat.
Okay.
So in the meanwhile,
Okay.
I'll just read out the first question. It's from Anand Kumar. I would again request all the participants to please mention the name of their country and their name and country name so that we can just inform the experts about that. So question is, what is the resolution of time series simulation that HOMER performs? If the load data is available at minute resolution, can HOMER simulate a hybrid system at minute resolution?
Yes. Here, I'll turn my camera back on. I guess it's. And I don't know. It's funny. On my screen, it's got my name next to Silver's picture. I'm not sure.
Yeah,
I don't know if everybody's got that.
Dr. Peter.
Not sure how that happened, but it doesn't really matter. That's Silver, and this doesn't matter.
I'm Silver.
Actually, Silver is connected through Peter's account. Silver, you should connect from your own link. That's how your name would then be visible on the screen.
Oh, I see. Huh,
Okay.
interesting. But to answer the question, yes, we can go to any simulation time step between a minute and an hour. So if you have 1 minute data, we can do that. Now it runs slower, obviously, because you're doing 60 times as many calculations. There's 60 hours in a year, and there's I think it's 525,600 minutes in a year. So it's obviously going to more. But if you have that kind of data, fine. A lot of times you have 15-minute data or 10-minute data, 5-minute data. We can do any of those things. Okay, what's the next question?
The next question is there any limitation regarding the size of system that HOMER can simulate a system of size like megawatts?
There's no limit to the size. There is a limit, and Silver, if you click on the converter, component, let's go to components, components and converter. Need to close that. I mean control. Excuse me. I meant controller. I'm sorry. And then click on any one of them, like cycle charging, load following. First show the drop down. Yeah. So we have 7 different control strategies. The defaults are these first 2, cycle charging and load following. And click on up above on the tabs, any one of them. On the tab, or yeah, there, click there, that's good. Either place. And so this is the limitation. It's not in terms of megawatts, but you can't have more than 20 generators. You can't have more than 10 storage devices, although Homer will only model one at a time. But with generators, you can have up to 10 different PV arrays, 2 different wind turbines. This is where the limitation shows up here. It's not in terms of megawatts. It's in terms of the number of components. But you know, we got an interesting result. And so how many questions are there?
There are like 3 more questions.
3 more questions. Well, I want to show this graph because it's one of my favorites. And it shows where, under what conditions is a least cost system doesn't have a generator, is 100% renewable, and it's the sort of yellow orange, I'm not sure what color to call that. So if the fuel price is high enough, or you can tolerate a little bit of capacity shortage or unmet energy, you can get rid of the least cost solution doesn't have a generator. But if you want 100% reliability, you need a generator. And if fuel is cheap, you know, it doesn't hurt to have a generator. But if you, on the superimposed variables in the upper left, Silver, if you put in fuel, either fuel consumption or total fuel, where is that? Down low, fuel, I'd go down further, total fuel there. You can see that even though you have a generator, it's only using, you know, a few thousand liters per year. And if you go back to the table, you see the generator only case, I think it was 30,000, 25. It was quite a lot more fuel. It was generator only case was using 27,000 liters. So, you know, even with inexpensive fuel, 80 cents a liter, and even if you want 100% reliability, the hybrid system is cutting your fuel consumption by, you know, 40%, 60%, or I'm just estimating. Yeah, something like 60% reduction in fuel consumption, even with inexpensive fuel and 100% reliability. So I really like that optimal system type graph because it gives you quickly answers some questions. And it's a question we get all the time is well, I don't want a diesel generator. Okay, well, you know, here's what you know it looks like without a diesel generator. So what's the next question?
We have a question from Rishesh Amatia. He's from Nepal Electricity Authority. His question is, why no cost changes at 5% capacity shortages with no fuel sensitivity?
As long as there is a backup generator, you can avoid any capacity shortage. I mean, what we're not modeling in this simple analysis is, you know, downtime on the generator for maintenance or, you know, breakdowns or something like that. And we can model that, but we're, you know, on the first day here, we're keeping it simple. So we're assuming, so if you have a backup generator, you're not going to have any capacity shortage. And if the least cost system for 100% reliability, well, that's not the right way to say it.
Yeah.
If it makes sense to have a backup generator, there's no advantage to allowing unserved energy. That I think is the simplest way to explain it.
Okay. We have a question from Haroon Shokat from Pakistan. His question is, can we use a non-grid PV system for reducing the initial cost by using HOMER Pro software?
So the question is, can Homer model on-grid PV arrays?
Yes.
Yeah, that'll be, which day is that? That's day 3, I think.
Day 3.
Oh,
Yeah. So we'll be talking about that on Wednesday.
okay.
Yeah.
Okay, so we have a last question from Ahmed Amar Yasser. Can Homer simulate gasifier-based generators?
Yes, it can. So if you look up top here, we have, if you go to resources, Silver, you can see biofuel, biomass is one of the resources. So there's a couple of there's a couple of different biofuels there.
And also for the fuel, you have different, you have biogas, you have other
biodiesel,
types of fuels.
methanol.
Yeah.
But if you go to the genset, go to a generator, and the drop down box, there's biogas. There's biogas. There's a couple there, but click on one of them and I can just show. We're not going to. This isn't part of the training. There, so if you're really interested in that, we could do something, not as part of this training. But if you have a biogas generator, so and every one of the components, I don't know if you saw there, Silver clicked on this blue advanced button over on the right. Yeah, there.
Yeah. Yeah.
So I don't know if you've noticed, those are all over the place. We've taken some of the, more detailed, more complicated stuff like maintenance scheduling, et cetera, and put it behind an advanced button. But for biogas, click on the biogas tab. So this is for a biogas generator, and I'm not actually prepared to go through all of it right today, but we could do that with you later.
Definitely.
Actually, it's interesting. I think there's a lot more work that's been done on biogas in South Asia than in many other parts of the world. So we'd love to talk with you more about that, actually.
Yeah.
Okay, so we have another question from Samir Ahmad. While simulating solar with natural gas gensets, solar sizing is limited with certain events like immediate cloud cover event, when gas genset has to take immediate load torque. Does this model help with that? Also, gas genset has maximum and minimum threshold limits, which needs to be input.
Yeah, so that's that minimum load ratio, which you can see right there on the left. So every thermal generator has a minimum load, and it's not just for efficiency purpose. I mean, the efficiency drops off pretty dramatically, and in a minute, Silver can show those efficiency curves. Right? Yeah, show it now, right now. And click on efficiency. I think that's easier for people to think about. So the efficiency really drops off with load, but not only that, there's a maintenance problem with running any kind of generator too low a load. You get condensation in the exhaust stack. There's a whole variety of problems in addition to it's just inefficient. So HOMER enforces a constraint on the minimum load on any kind of generator, gas, diesel, whatever.
Okay, I think we are over with the questions, so you can carry on with the rest.
Right. Well, that might be all the prepared material we had. So I'm wondering what would be the most useful way to use the remaining 20 minutes.
There were certain queries from the participants on these code or this number which you had shared in the text box. I think if you might explain it to them how to register for the software.
The concurrent licensing?
Yes.
Yeah. So, I don't know. Silver, you want to click on help license? Or I could take the screen, I guess.
Yeah, you can take the screen, Peter. How do I?
Hold on, let me get HOMER Pro up on my computer here. Thought I had. So it might look a little different on your computer. Here, let me. Actually, I'm not sure which screen I'm gonna. when I share this, show my screen. Oh, here we go. Okay, so actually, let me close. Let me close. Ah. Yeah. Let me move that out of the way. Okay, so when you first open Homer, I think Silver has clicked this button so it doesn't see this every time. But when you open Homer, you get this screen, which is really nice. For example, the setup assistant is a way to just click through very quickly, answer just a couple of questions, and get a result. So I like showing that. Although I probably should, yeah, let me cancel. And I canceled it. But to go back to the question about how to use that number, your screen might look a little different. I mean, I've got an active license, so I'm not sure exactly what your screen will look like, but it'll have this button down at the bottom here that for concurrent. And this is where you cut and paste, where you paste in or type in that big number. Which I can put that back up, I think. If, yeah, hold on.
You might
Yeah.
want to show that presentation page where we have the code and the page where it shows the steps. So they would need to enter. They would need to enter their email ID. Yeah, this one.
Right. So Needy, this is what it looks like if they don't have an active license. Is that?
Yep. Yes.
Yeah.
So when they open it for the first time, they are going to see this one, and they do not have to click on this get started option, which they might be getting.
Right. There's another box here that I've covered up. And he's like to say, don't click here. So yeah, you need to type your email address, and then this is where you paste this number in here. Right. So I really hope you all have been able to download it, and then if you this will and so then you can run it here. That's very useful.
It's also important for the participants to get the software downloaded and installed on their systems, because I guess from tomorrow onward we would have physical exercises. We would like participants to go along with in feeding all these data into the software while the experts will be explaining the demonstration of the software. Am I right, Peter?
Yeah, well, with this many people doing it virtually, it's a little harder to go back and forth with, having the attendees do an analysis. We provided all the files though, right? You shared that zip file that has sort of the completed, sort of mimics what Silver was doing. So that makes it easier to because what invariably happens when we're doing a training, even with just 6 or 7 people, is it's really hard for everybody to move along at the same pace. And sometimes, people will type in a wrong number, or they'll do something different, and they'll get a different answer. And then, since we're building each lesson built on the previous one, if they don't have the right results from lesson 3, then they're not going to get the right results in lesson 4 either. But that's why we supplied those files. So this is the right results, with the right inputs, etc., for each of the lessons.
Yes.
So, like, for example, I just opened lesson 5, which was the final one, which hopefully has this nice Oh, I have to calculate. Oh, shoot. So it'll take a minute. But it'll have that nice, what we call the OST graph, optimal system type graph. And so tomorrow, we'll, right, Silver, we're going to start with this file and build on it, right?
Right.
Yeah. So
what we can do is that just for the information of participants, all these files will be uploaded on our website link. You can download all those materials from our website. And as Peter mentioned, that it's very difficult to stay in with the speed or with the content that Peter is sharing or this Silverio is sharing. But what participants could do is to just follow the lead and try to grasp as much information as they can. And in their leisure time, then they can go on with experimenting the software. So this whole exercise is just to give you a flavor of this software and how it works, just to make the understanding.
right, and I think we have the manual there as well. And I'll just bring it up in my version of it so you see what it looks like. This is in that zip file. This file here is in that zip file as well. And Silver's basically walked through this, and it's funny because it's way past my bedtime here in the U.S., but it's morning for you, so you have the rest of the day to look through this manual and look through those files and see if you can replicate what we've done.
Yes.
Yeah, so here's the result of let me make this bigger. And so one thing that I really like about HOMER is it goes to that simulate, optimize sensitivity analysis sort of approach that we have. This is at the highest level. This is some very high level results from the sensitivity analysis. These are our two sensitivity variables, and it's just showing what's the optimal category or system type. But then if we go over here to tables, we have the sensitivity results on the top. This is the least cost system for each one of these sensitivity cases. So these are, we did an optimization for each one of these cases here. The first two columns define the sensitivity case. And this upper table is just showing you the least cost system for each of those cases. But if we click on any one of these, let's say, I don't know, let's say this one here, because it's a 100% renewables case. No, let's just take, I don't know, let's take this one. Just to be, now the lower table is showing you the optimization results. So this is the sensitivity analysis, this is the optimization results, and this is showing you the this upper top system here should be identical to this one, because this is the least cost system of all of these cases. And remember, there were hundreds of cases here, right? But we categorized them. So this is the least cost PV diesel battery. This is least cost just battery diesel. Here's the diesel only, etc. And then if we double click here, we can look at the simulation results. So we have simulation, optimization, sensitivity, and there's a lot of details here, like showing most of the energy came from PV. I think this was an area that didn't have a lot of seasonality to the solar resource or to the load, so that it doesn't change much over the year. People really worry about this excess electricity. There's almost always some excess electricity because you can't really control when the sun shines, and the batteries will be full sometime, and that's it sounds wasteful, but it's sort of inevitable that you'll have some. But you can look at, so how's the battery doing? You can really see that it's cycling. And here's what I really like. HOMER's generated a huge amount of data. just to show you here in table form, you can look at how did this system, let me expand this. How did the system operate for every hour of the year, or as that other person asked, you know, it could be every minute of the year. And here's all the variables that changed, you know, from hour to hour, you know, that Homer's modeling. This is a bit overwhelming, but you can export it to Excel. There's a variety of ways to look at it. But this is probably one of the best ways, is this time series plot. Let me wait till it, my computer's really slow this morning, or this evening, whatever. In fact, let me see if I can close some things down. So, and you can zoom in here. I'm just dragging across here to zoom in and look at how things operated from day to day. So the dark one, that's the load. The PV output is brown, so you can see it's, you know, it's really producing in the middle of the day. The batteries are charging when the sun shines and discharging at night, but sometimes the generator comes on, and so the batteries can stop discharging just because the load happened to be really high then. And there's a huge number of variables here. We're not showing them all. You know, we're trying to keep things from being overwhelming, but you can graph all kinds of things, and you can put things like the battery state of charge, you know, you put that on a second graph. So you can see here, it was kind of a cloudy day and the battery never really got recharged very well, for example. And then you can look at it monthly. That's just the solar resource monthly, but if we, you know, you can look at any of these things, either monthly, or here's the daily profile, that's 24 hours for each month. We created this thing called a DMAP, which we think is really handy because it has data for the entire year here. So you've got your 365 days of the year along the x-axis and your 24 hours of the day along the y-axis. So each little triangle, rectangle here is an hour, and a day is a vertical line. And you know, as you can see by hovering over it, we can see what the values are. So that's what the load looks like over the course of the day. Here's what where's the PV output? Well, that's what the the solar resource, well, the production, PV production looks like. So you can see, you know, we have some cloudy days here. We have a real sunny period here and here. And what's the battery doing? Well, let's see, this, whoops, that's not what I meant to click on. Here we go. So the red area, here's the legends over here on the right. The red area is with the battery is fully charged. So in the winter time, in this location, the battery is getting really fully charged every day. But here in, I guess it's like July, there's a few days where the battery really doesn't get fully recharged. This must be the rainy season. So we think this DMAP is really handy. You can look at it as a probability distribution function. So the battery, actually, for the battery is sitting at its minimum state of charge, you know, not too often, but fairly often. And it's not, and it's, well, actually lead acid, well, and it's often hard to get a battery 100% state of charge because its ability to absorb charge slows down as you get near the top. But anyway, the battery is clearly being used a lot. The duration curve is something utility companies really like. They talk about load duration curves all the time. So if we look at the load, that's a load duration curve. So you can see there's the peak periods aren't very long, and then there's this whole intermediate period here. And for this one, but anyways, this is a commonly used graph in the utility industry. Maybe not so much in the microgrid world, but we provide it anyway. And all of these variables can be plotted with any of these kinds of graphs. So we really like this ability to really dig in and see how did the thing operate. And if you have a graph that you created a graph that you really like, you can save it over here. Well, you save it with this button, and then it'll show up in this list over here. So these are ones we have created, and provided with the software. So there's just a lot of data that HOMER generates, and this is called the foundations training. We're just giving you the enough to get started, but you should explore it on your own. Were there any more questions that came in?
Peter, I think we don't have any more questions. We are over with the session. If you have anything to add, we can.
Well, tomorrow we're going to do more detailed analysis. We're going to look at different ways to optimize based on specific sizes, and dig into the cost table, how you can so we'll just get into a lot more details tomorrow. Silver or Needy, is there anything either of you want to add?
I don't think so. Silver, you're muted.
Yeah, Silver, you're still muted.
Silver is, I think, muted.
Well, oh, there you go. No, you might be able to unmute him. Silver, can you unmute yourself?
Okay, yeah. I would recommend the participants to download the software using also the license that was posted by Peter. And with the manuals that we provided, they can try simulating what we did on their own time. And it will also be good as they watch our presentation, they do also their own simulations.
Right. So just so you know, on our website, homerenergy.com, you can go here to HOMER Pro. Whoops, sorry, HOMER Pro download. You have to create an account. I already have one, so it won't look the same for you exactly. But that's where you download it, and then Silver mentioned this in the beginning. Under support here, we have lots of different ways to get support there, and we mentioned this: the user manual, the video library, there's a knowledge base, there's training. You can hire us to do projects for you or for advanced training. So the video library is very popular. Some of those videos need updating, but they're still, so the screenshots might not look exactly the same, but you get them. They're still helpful. So that's all I've got for this evening, or this morning.
Okay. So I think we may now like to conclude today's session. Thank you everyone for attending the training. We had listened to some excellent presentations delivered by our distinguished presenters. I'm specifically grateful to Dr. Peter as he's delivering this training at midnight now. Plus all the presentations and the contents will be available on our website. I've already shared the link on the chat box. We will meet tomorrow again at 10:00 hours Pakistan Standard Time. You can use the same web link to get connected for tomorrow's session. So, ladies and gentlemen, with me signing out, thank you again for joining us today and looking forward to see you tomorrow. Bye-bye.
Yes, see you tomorrow.